Welcome students. Today we are going to see the concept of uniform continuity. Now we know the definition of continuous function. Actually in continuous function we use epsilon delta definition. We use epsilon delta definition. It means that for given epsilon greater than 0 we can find a real number delta greater than 0 such that mod of f of x minus f of x naught is less than epsilon whenever we have mod of x minus x naught is less than delta here. So that tells us that here now delta depends on epsilon and x naught also. So let us see that. So first we see now definition of continuity here. So continuous function. So here now these are the two matrix spaces. So let xd and y row be matrix spaces. Be matrix spaces. And let f from x to y be a continuous function. Be a continuous function. Then for each x naught belongs to x, that is for each element of this set, and for a given epsilon greater than 0 there exists a delta greater than 0 such that we have here now d of x naught is less than delta. So this implies that we have now rho of f of x naught is less than epsilon here. So now if x naught is fixed and epsilon is made smaller, okay, then in that case the delta greater than 0, now this one has to be made smaller correspondingly. So if we consider now this one, so if we take now f of x is equal to now 3x, now this function, now f is function from Ru to Ru, then now here mod of f of x minus f of x naught here is equal to, we write here 3 into, actually this is 3x minus 3x naught, now this is less than epsilon. So this implies that we write here now mod of x minus x naught is less than epsilon upon 3. So it means that here now in this case now delta greater than 0 can always be chosen as any number less than or equal to epsilon upon 3 here. Okay, so this tells us that now delta depends on epsilon here. That is now this real number delta depends on real number epsilon. So if we keep now this epsilon fixed and move to another point from which is different from x naught, then in that case it may happen that now this delta no longer works. Okay, that is it may be necessary to take smaller delta greater than 0 to satisfy the requirement of this definition here. So in this way we observe that delta in general may depend on not only on epsilon but also on x naught here. Okay, now the uniform continuity is the idea or the concept of continuity with added condition. That is, for each epsilon greater than 0 we can find a delta greater than 0 which works uniformly for the entire space x here. Okay, for the entire space x it means that delta does not depend on the points x naught but only on epsilon greater than 0 here. So now we are going to see now definition of uniformly continuous function. Okay, now here one thing is again important here. Now that thing is, now remember that here actually here one may think of choosing the smallest delta greater than 0 out of the among available deltas for different points of x here, but such a smallest delta which is non-zero here may not be always available, and therefore every continuous function may not be uniformly continuous. So first we are going to see now definition of uniformly continuous function, then we discuss all these things. Now uniformly continuous function. Definition: let xd and y comma rho be metric spaces, a function f from x to y is said to be uniformly continuous if for given epsilon greater than 0 there exists a delta greater than 0. Remember here, now delta depends on epsilon alone, that is delta depends only on epsilon here, such that d of x dash, now this is less than delta for x and x dash belong to x, implies that now rho of f of x dash, now this is less than epsilon here. Okay, now remember that when given function is uniformly continuous, then that function is always continuous function, but the converse is not true. Okay, that is continuous function need not be uniformly continuous. So we are going to see one example here. Now example is that now here f is the function from now ru to ru, okay, where r is the set of real numbers, and ru it means that this is the r with visual metric d of xy is equal to mod of x minus y. Okay, now here now function is this one, f of x is equal to x. Now this function is continuous function here. Okay, so now the graph of this function is now this one. Okay, so this is the graph of function f of x is equal to x square here. Okay, now function f is continuous, but this function is not uniformly continuous. Okay, because here we are going to show that there exists an epsilon greater than 0 for which no delta works here, no delta works. Okay, now taking here now epsilon is equal to 1. Okay, and let delta greater than 0 be given here. Okay, so in this case now we take 2 points here. Let x1 is equal to now delta upon 2 plus 1 upon delta, and x2 is equal to we take 1 upon delta here. Okay, then we have mod of x1 minus x2 is equal to, now this is delta upon 2 plus 1 upon delta minus 1 upon delta. Now this is plus 1 upon delta minus 1 upon delta is 0. So we write here mod of delta upon 2, which is equal to, we have delta upon 2, which is greater than 0 here. Okay, and mod of x1 minus x2. Now this is delta upon 2 and this is less than delta here. Okay, but here now for mod of f of x1 minus f of x2, we have here, now this is delta upon 2 plus 1 upon delta bracket square minus 1 upon delta square. So here we can write here now delta square upon 4 plus now product of these two. Okay, so 1 upon delta into delta upon 2 into 2, that is we have plus 1 upon delta square minus 1 upon delta square. So this is 1 plus delta square upon 4 here. Okay, so this is greater than 1 here. Actually we write this. So therefore, thus whatever delta may be here, now there exists, now here x1 and x2 belongs to R such that now we have here mod of x1 minus x2 is less than delta, but yes, here now in this case mod of f of x1 minus f of x2, now this is greater than 1. So now this function is not here uniformly continuous. So f of x is equal to x square. Now that function is continuous but not uniformly continuous here. So now we are going to see one theorem. Now next theorem is that let x comma d be a matrix space. Be a matrix space and A be subset of x. Then the function here now f from x to r, that is this is real valued function given by now f of x is equal to now d of x comma a, that is distance between point and the set here where x belongs to x here, is uniformly continuous here. Now we are going to prove that now this function is uniformly continuous. Now proof of this theorem is now here we have, now this is the matrix space and f is a function from x to r which is given by in this way. So if we take now here points of set a and x here, that is if we take now here 3 points here, then by using triangle inequality we write now this one. So by using triangle inequality we write here d of x comma a, this is less equal d of x comma y plus d of y comma a for all a belongs to a and x comma y belongs to x. So we write this because we know that x comma d is matrix space. Okay, then on taking infimum here, infimum here, okay, for this set a here, okay, on taking infimum of all these values, okay, we get here, now d of xk infimum of this one, sorry, okay, this is always less equal d of xy plus infimum of d of ya. where this infimum is taken over all elements of this set A here. So we write this. Now remember here, now we are not writing this because d of xy, now this is independent of A here, or d of xy here, now this is independent of this element here, okay, element A here. So therefore we write here d of x comma A. Actually this is the definition of distance between set and a point. This is less equal d of xy plus now d of y comma A. So this implies that we write here now d of xa minus d of ya. Now this is less equal d of x comma y. Now this is true for all xy belongs to x. Remember this is true for all xy belongs to x. So therefore on interchanging, now here x and y, okay, we write here x and y, we get d of ya minus d of xa. Now this is less equal d of yx, that is we have d of xy. By using symmetry we write this. So you can take now minus 1 common, so we write here minus 1 into, we write here d of xa minus d of ya. Now this is less equal now d of x comma y. Thus we write here, okay, now we know that d of xa minus d of ya, this is less equal d of xy, and minus of d of xa minus d of ya, this is also less equal d of xy. So therefore we write here, yes, absolute value of d of xa minus d of ya. Now this is less equal d of xy. So therefore for a given epsilon greater than 0, yes, choosing a delta such that 0 is less than delta is less equal epsilon. We have now mod of f of x, or absolute value of f of x minus f of y. Actually this is absolute value of d of xa minus d of ya. This is less equal now d of x comma y, okay, this is less than delta, and this is less equal epsilon. That is, we write here now absolute value of f of x minus f of y. Now this is less than epsilon, okay, this is less than epsilon whenever we have d of x comma y is less than delta. Hence, okay, delta depends on epsilon only. So therefore we write here, hence f is uniformly continuous. F is uniformly continuous function. Now next theorem is about now Cauchy sequence and uniformly continuous function. Now this theorem tells us that image of Cauchy sequence is Cauchy sequence when the given function is uniformly continuous. So statement of the theorem is this. Theorem, let xd and y row be metric spaces, and f from x to y be a uniformly continuous be a uniformly continuous function if now this sequence xn is a Cauchy sequence in X, then its image, that is f of xn under f, is a Cauchy sequence in Y, is a Cauchy sequence in Y. Now in this case, now this function f from x to y is uniformly continuous. Now xn is a Cauchy sequence, then we want to show that now its image under f is a Cauchy sequence in y here. So we are going to use this. So we write here, now since f is uniformly continuous, now this function f is uniformly continuous, so we write here for a given epsilon greater than 0, there exists a delta greater than 0 such that now d of x dash, now this is less than delta, where x and x dash belongs to x. Now this implies that yes, rho of f of x dash is less than epsilon. So this has now 1. Okay. So in particular, we write here, in particular, we have here, now if we take x is equal to xn and x dash is equal to xm, then we write here, now d of xn xm, now this is less than delta. So this implies that we write here rho of, okay, f of xn, f of xm, now this is less than epsilon. So this has now 2. Now we know about the sequence xn here. Now xn is a Cauchy sequence here, so we use that. So I am writing here, but xn is a Cauchy sequence in x. So given delta greater than 0, yes, there exists a positive integer, capital N, such that we write here, now d of xn xm less than delta for all m and n greater or equal n. So by using definition of Cauchy sequence, so we write this. So this is 3. So therefore from now in this case from 2 and 3 here, 2 and 3. Now from 2 we have d of xn xm is less than delta. Now this implies that rho of f of xn f of xm is less than epsilon. Okay, and here now from 3 we have d of xn xm is less than delta for all m and n greater or equal n. So using this, yes, we write here rho of f of xn f of xm. Now this is less than epsilon for all m and n greater or equal n. So we write here, hence actually this is the definition of Cauchy sequence. So we write here, hence f of xn is a Cauchy sequence in Y. Cauchy sequence in Y. Thank you, students.